Welcome, everybody. Our guest is just connected now. So we will start our activity. It's a pleasure to have you all connected today to this small spontaneous activity that we organized. It's welcome to our class of Introduction to Astronomy from the University del Valle. My name is Eduardo Rubio, and I will be hosting together with Dr. Rodrigo Sacahui from the University of San Carlos this spontaneous meeting that we will have with our special guest who just came a few minutes ago. Welcome. And first of all, I want to say to him, herzliche willkommen in Guatemala. Bienvenido a Guatemala, Didier. Today, we have the pleasure to have a very special guest who will be attending, giving us a small presentation. The guest is the Professor Didier Queloz. He's from the Polytechnic Federal Institute in Switzerland, in Zurich. He also is a member of the University of Geneva in Switzerland, and also was a former professor at Cambridge in England. He is known in the world of astronomy because he was together with his former PhD supervisor, Michael Mayer. He was the first one to discover the first planet in another star, 51 Pegasi. And thanks to his works in searching for exoplanets, he has won many prestigious awards, such as the BBVA Foundation Frontiers of Knowledge Award of Basic Sciences, the Wolf Prize in Physics. He has been elected recently a member of the Royal Society in England. And last but not least, in 2019, he shared the Nobel Prize of Physics together with Michael Mayer and James Peebles. So Didier, welcome. I hope you can hear us. I made you co-host now. So I think you can start your camera, and I will remove these slides so you can share your presentation with us. So welcome everybody, and Didier, it's a real pleasure to have you here, and we look forward to have you here. I think you have full rights to share.
You.
Really welcome.
Thank you very much for very nice welcome. It's a pleasure to be with you remotely. Actually, I am in Cambridge. I'm not anymore in Geneva, so I am a Cambridge professor and also a Cambridge at ATH, which is the Zurich École Polytechnique. Right, so what I would like to do with you is to share what we used to identify as the exoplanet revolutions. And you will understand why it's a revolutions because it is going to possibly answering one of the big questions of that we can think about is the origin of life on Earth. So let me share my slide if it works. So you should see my slide, and if I do that, you should be seeing my first slide, right?
Yes, I can see it, Didier.
Fantastic. So I'm going to minimize all that, then you don't need to see that. Okay, so so let's give it a start. Right, so I mean, usually when you talk about planet, we all have in mind these planets. This is a planet of the solar system. And it's interesting to keep that in mind because they are still a reference to us. And when you think about this planet, they are also a big puzzle. How do we end up having such a different kind of planet in the solar system? And to understand that, you have to open a planet in a way. So if I open here Jupiter and I open Neptune's, what you would find in the planet, and that's something we have found by probes, by studying the gravity of these planets and modeling the interior, is the big planet. They're essentially full of gas, the hydrogen, the same gas you have in the sun. And in the middle, you have a core, a very solid core, which is the seed of the planet. So that's thanks to this core, the mass of this core that attracted all the gas around and ended up being a giant planet. So the planet, like the Earth, has no gas, essentially. It's only the core because it was formed late in the system. And Neptune was, in a way, a failed giant planet because it had a smaller core and didn't manage to attract a lot of gas. So how do you make planet practically in a system? So to explain simply the process, I will use beautiful picture that we have of young star with planet formation. This is one of the stars you have in the sky, HL Tau, and this is observed with a wonderful telescope. It's actually a series of antennas. We call that ALMA. It's on the Altiplano in Chile. And these antennas observe the sky and combine the observations at a very far wavelength, which is similar to the wavelength you have in the microwave. And it is sensitive at very cold objects. So what you see here, it's a cold object, but hot enough to be visible. So it's a heat, if you want. You see, it's a thermal radiation of the object, about 60 degree Kelvin out of the 0 degree absolute. So the star is the middle, and around you have a disk, and that's how you make planets. You see there are structure in the disk, because when you make planets, you create waves, and you can imagine that even some of the structure is a result of a planet that is going to attract the gas around, making this kind of grooves you have here, if you see my around the planet. So this is the size. So it's about the size of the solar system, and we have example of such a star. They're very young. It's about 10 million years old, and what you do see is the thermal irradiations from all the tiny particles you have in the system. So what you don't see is the gas that is not visible like that, and we have to make a trick to see the gas. So to understand a little bit the formation of the system, I will observe another star, which is in the southern hemisphere, which is the star Beta Peak, for which we know that the disk is seen on the edge. So you really see the disk on the edge, and you get a feeling in the visible light. This is not the thermal irradiation this time, it's a reflected light. So it's like the moon reflecting the light of the sun. And you see the disk is very narrow and not very elongated in the vertical directions. You can even see another disk here because there is a planet orbiting that star, and you don't see the star because we have on purpose added a mask not to be blinded, because the star will be extremely bright here. So my point here, a disk is very big, but it's very thin. And the reason why it's very thin is because the gravity of the disk is such that all the particle is oscillating here and stay all together on a very thin layer along the disk. Now, when you look at the same disk at the same size, but you look at the gas, in that case, you're using ALMA again, but sensitive to the absorption line of the CO2 gas. And what you would find out is this structure. So there's a big difference here between the gas structure and this structure, which is the result of all the tiny particle, all the solid particle you have that is reflected the light. The first one is it's way more extended vertically, and there is a good reason for that. It may remind you, this is called the hydrostatic equilibrium. There is a balance between the pressure and the gravity that prevent the gas to fall. It's why when you go to the mountain, you can still breathe. Well, if you throw a stone out of a mountain, well, it will go down to the bottom. So there's nothing that stops the stone to fall until it reaches the bottom. The gas will stay because there is some pressure that will maintain the gas. So the gas is way more extended than the particle. Bearing in mind that the gas, there is way more gas than there is particle. There is about 100 to 1,000 times more gas, essentially hydrogen and helium and water and all the gas you can imagine that you have of particle. Now, the other big difference here is there is a limit where you will see no gas. It's not because the telescope is not good enough. Actually, there is no problem to detect the gas B1. It's just because there is no more gas. So how come do you have the disk here that continues and here there is no gas? Well, if you think about, then there is the sun here, there's a star in the middle. So there is a difference of temperature if you're very close to the star or if you're very far away. There is what's called a thermal gradient into the disk. And there is a point when it becomes cold enough where the gas, it cannot stay as gas. There is a phase transition for most of the gas, except for the hydrogen, but for most of the other gas. And then you have snow. You can imagine that the water gas is quite a lot in water gas in these disks. And it means it's essentially snowing. Practically, it's really literally snowing in this area. So there is a distance where the gas cannot stay as gas and become a particle like this one. So you have to imagine, because it's a particle, everything is going to collapse. So you will have an amazing quantity of matter that collapse at some distance here, way more than all the other parts of the disk. This is why we have a very speedy formation of the planet outside the solar system, because there's so much particle that is falling, it's snowing. So you build a core very rapidly, and you build the core so rapidly that you trap the gas which is left around that never frost, which is the hydrogen. And that's how you make Jupiter. This is why we have Jupiter outside of the solar system. This is called snow lines. And what I'm telling you here is the foundation of the planet formations, and there has been a lot of modeling, and that explains very well the solar system. Now, when you understand that, what I'm going to tell you is the reality is way more complicated, because the first planet that we have detected was it 26 years ago, was a Jupiter planet with a lot of gas then, but the planet was not there. The planet was very, very close to the star. That's what we call a hot Jupiter. And that was an absolute shock for the community. And it took a couple of years for the community to be convinced that the planet was really existing. So what I'm going to show you right now is the new picture of our understanding about planet. So I'm using only 3 parameters. All the point you have on this picture is a real observation. It's a real planet that we have detected. We know the mass, we know the size of the planet, and we know the period. The blue is being by using the transit, when the planet goes in front of the star to be detected. The red is when you use the motion, the change of the motion or change of speed or radial velocity from the star. Well, the planet I was talking about, 51 Peg, belongs to that category. It's 10 times the radius of the Earth. This is Earth radius, so it's about Jupiter. Period, a few days. We have radius here, we have the mass about Jupiter. You see Jupiter here, and also a couple of days of period. So this is really a mystery. We have planet more alike we would expect, like this one here, like Jupiter. There's not much size for this planet because they are very unlikely we detect the transit. So to understand then this diagram, I have to add one extra piece of information, is the limit of the technique we're using. So this is a line of the limit. So anything which is on the left side can be detected. Anything which is on the right side cannot be detected. So we don't detect very easily a transiting planet at long period because it's very unlikely you see a transit. You have a transiting configurations. And we don't detect a planet like the Earth at the period of the Earth. We do detect Earth size, it's no problem, but they have to be very short distance. So this is a severe limitation right now of the techniques, both on the transit and the radial velocity. We don't have such a discovery yet because we just can't, it's too difficult. So we're working on that, and they will be in the next 10 to 20 years. But already what we have found is amazing because we have detected clearly planets like Jupiter with some more clearly bigger. And when you have a Jupiter here and then you have a planet there, it means it's 10 times more massive than Jupiter. So there is really a huge diversity of planet here. But what was really a surprise is this group of planet here or there, because they are sitting between the Earth size or the Earth mass and the Neptune size and Neptune mass. We used to call that the super Earth or the mini Neptunes, and they all pay well attention on a very short period, like a couple of days, 10 days, 20 days. So most of them are very hot, and they have no counterpart in the solar system. The only planet we have in the solar system is Mercury, but Mercury is much more smaller, and that's farther away. We don't have, Mercury is not a 3-4 days period. So this is really a surprise, because nobody would have guessed that we would have had such a planet. And what is even more fascinating about the discovery is to ask ourselves, what is the occurrence of this system? It means when you observe the stars, what is the chance that I have any of this planet orbiting? And this is a kind of a complicated computation, because you have to account for the systematics, for the target you observe. But there are some kind of a common agreement on these numbers, and these are the number that people are coming. Is for the hot Jupiter, it's a few percent. So it's still rare to have this very big planet. There are quite a lot being known because they are easy to find, but actually they're not that common. The planet like Jupiter, more like Jupiter, seems to be more common, about 10 to 20%, while the category we're talking about is where broader. You have clearly planets that have shorter periods. Some of them have the orbit of the Earth, and you do consider also a planet that are more massive than Jupiter. So the exact Jupiter, they may not that many, as you see on this diagram. But the big surprise is the occurrence of that kind of category here. So essentially what this number is telling you is when you observe the sky, when you point a star like the sun or similar to the sun, there is 50% chance that on that star, you would have an orbiting planet like that, which is quite of a shock when you think about it, because everybody expected a planet like the solar system. And actually what the nature is telling you is, no, I think most of the planets are different. It does not mean that the solar system is rare. It just means that the majority of the planets are different from the solar system. And they belong to this category of very strange world that is the mini Neptune and super Earth. Now, what is interesting here is because they have short period, we have been able for some of them to have both the mass and the size. And you see on this diagram, the blue dot are the transit discovery, and the red dot are the mass. And there's clearly blue dot on the size of the mass, and there's a red dot as well on the size of the blue. So there is common observation for the same planet of the mass and the size. Well, if you have the mass and the size of the planet, you have the density. And I would like to share with you the plot of all the planets for which we have both the mass and the size. And that is this diagram, where the mass is on the bottom in Earth mass. 300 times the mass of the Earth is Jupiter. And here they have the radius, and 10 times the Earth radius is Jupiter. So you see Jupiter, Saturn, Neptune here. So you see a lot of dots with kind of a crosshair sign to indicate the error bars. And you see a kind of a trend here moving down into the size. So to help you a little bit read that, we used to superimpose the bulk density that you can compute for known planets. So the obvious known planet you can use is Jupiter. So you take the density of Jupiter and the density model of Jupiter, and it would sit along this line. So you do see that if you start off with Jupiter and you decrease the mass, you are going to meet Saturn. You do have some object, even smaller, that would match this density, but essentially all the known hot Jupiter, they're lying above in this diagram. It means for a given mass, the size will be larger. So if you keep the mass the same, but you increase the size, you're going to decrease the density. So all these hot Jupiter, they are so-called inflated. They're bigger, slightly bigger than they should be with Jupiter. Frankly, we don't know very well why, but we do suspect it's because the surface temperature is so hot that it is changing some physical structure, internal structure of this planet, and the planet is responding by being a bit inflated. Now, what is fascinating in this diagram is we do have a lot of smaller Saturn, but when you reach the mass of Neptune, you clearly not reproduce Neptune density with the Jupiter model, which is expected because I said earlier that Neptune is a kind of a failed Jupiter because it failed to attract all the hydrogen that Jupiter managed to get. So in a way, Neptune has denser gas, all the gas that they managed to trap essentially from this famous snowball effect, the snow effect, but didn't reach the stage where they managed to attract a lot of hydrogen, and in a little bit, but not too much. That's why it's denser. Now, for the same mass than Neptune here, you do have planet that is clearly inflated, and that would qualify as Jupiter, but you also have planet which is way denser here. So to help you read that, we have added here a kind of a hypothetical density diagram, which is a planet that doesn't really exist, but could be made of water. So imagine you make a planet only of water. So you would lie along this kind of line here. So give you some kind of idea of what looks like a Neptune-ish planet. And we do have quite a lot of them, even of much smaller mass. I mean, look, we can go up here, up to 2 times, 3 times Neptunes, but we can go down to almost 2 Earth mass. So there is really small planet which has almost the mass of the Earth, that doesn't seem to be very different in terms of structure to Neptune's, but clearly different from the Earth. So to meet the Earth, you have to go to this green line here. This is 1 Earth mass, 1 Earth size, and you can go up, and you see we do have clearly detected planet that would qualify clearly as density Earth-like. And there is a regime between the two when we see there is a kind of a lack of discovery here, detection that is real, that may be telling us that some of this planet may be in a transition, in a sense that you have a planet there, and because it's very hot, I remind you that most of the system are orbiting on a very short period, so they're too hot, so they're losing the atmosphere, and they start here and they ended up there. So it doesn't mean that it is a planet that is being formed like the Earth. It could be a planet formed like Neptune, that is losing its atmosphere. So we have an extremely complicated situation right now, where when you have a planet which has about the mass of the Earth, you're not sure it's an Earth, and you have clearly here data that demonstrate this. So all this is data. There is no modeling. The only model here of the hatchet line. So what is the conclusion of that? Well, we have to change the way we see what looks like a planet, and this is a new version right now of the understanding of the diversity of the planet structure. We still have Jupiter, we still have Neptune, we still have the Earth, but in between them, we have plenty of other, let's call that categories of planet. You can have something in between having Neptune's and Jupiter with a much massive core, but we could have a lot of diversity between Earth and Neptune. You can even imagine you have a Jupiter that is smaller than Neptune, so gas dwarf. You can have Neptune, you make it smaller, and you have these 3 sets of structure. You remove the outer atmosphere of Neptune, you have an ocean planet, what we call ocean planet. Or you have something like the Earth, which is essentially a rocky planet with a very, very tiny atmosphere, but much bigger. So this is a new reality. The challenge here is, as you've seen, to really understand what we're talking about here, because you can play with the size and the mass and having different structure corresponding to a similar mass or similar size. The way to make progress is trying to understand what is made the atmosphere of the planet, because you see here there is a very different atmosphere depending when you look at there's this one or that one. That one has essentially no atmosphere, the first order. This one would be an atmosphere of water. This one would be an atmosphere of gas, essentially hydrogen. And this one will be a mixed of atmospheric composition here. So how do we get the atmosphere of this planet? And that is really the hot topic. And it's a topic that started to develop. I mean, the first atmospheric detection of a planet is almost 15 years old. But with the launch soon of the James Webb Space Telescope, which will be the biggest ever flown space telescope, there will be plenty more of this planet that we can measure. So how do we do that? Well, we use a transit. So the transit, as you know, is when the planet goes in front of the star. We just got lucky and we have this configuration. But if the planet goes in front, there is a time when the planet is behind. So if you think about that, when the planet is behind, that's the only moment when you only see the star. And we're using this feature. So when you observe with the telescope, the star, what you have is a light curve. So this is a flux you have here. This is a time in phase. So it's folded on the phase of the planet. And you have the flux. So there's the time when you have the transit. So you have a drop of the flux from the star because the planet acts as a shadow. But you have the moment when the planet is just behind. So if you zoom in, which is the picture on the bottom, this moment here is where you only see the star. So if you only see the star, it means that up to that level, it's only the flux from the star. But the rest is the planet. So when we do that, actually, we do detect directly some flux from the planet. And when you do see here, it's called the day and night side effect. This is a day side. It's much more flux just before that the planet goes behind. So you see really the bright side of the planet. And then when you have the planet passing in front of the star, then you see the dark side. You see the side of the planet, which is just opposite, facing the one from the star. And from that, you can study the different nature of the atmosphere. From that, you can study the temperature of the atmosphere. And depending on the wavelength you observe, you can see clouds. You can even see the motion of the clouds on the atmosphere. So that's very powerful techniques to observe what's called a phase curve of a planet. Now, coming back on the transit, we can do way more than just observing the transit and getting the size, because the size of a planet depends on the wavelength where you observe the transit. I will show you that with an example. This is one picture of the ISS where you have the Earth, which is a planet, and we will pretend that the moon is a star in that case. Well, you see this tiny bluish layer here. This is called the Rayleigh diffusion. This is what makes the sky blue. And that's about 20 kilometers. So we have here a kind of a 20 kilometer size. So if you observe the star, the planet, and the Earth in the visible, you do see this because the Rayleigh is what essentially dominates the visible. Well, if you observe in the infrared, what is commonly done by the spy satellite, and they don't see the cloud, they only observe the surface of the planet. So you would see the planet without the atmosphere, and you will see the planet look smaller. So I move in infrared, it's slightly smaller. You don't see anymore this kind of extension here. So the very same transit observed in the infrared would end up with a smaller planet. Now, what I could do is I could do the extreme. I can use a wavelength which is sensitive to the upper atmosphere, where you have the ozone. It's about 50 to 60 kilometers. The very same picture with the ozone would be like that. You see the planet is much bigger when you compare it to the moon. So playing with a wavelength, you observe different size. And then you can do what's called a retrieval. So you can return this problem on the other side, and that will give you a kind of a stratigraphy or X-ray of the composition of the atmosphere, and that's the way we know a little bit the structure, the pressure, the thermal structure, and also the composition of the atmosphere. It's called the retrieval techniques. So when you combine these techniques, which is transit spectroscopy, with the phase function I described before, you can get a pretty good idea of the atmosphere of the planet. The only difficulty here is if you have a tiny atmosphere and a small planet, the signal would be very small. but it's just a matter of size of telescope and sensitivity. So you can ask yourself, with this, we should be able to detect life, to detect atmosphere of a rocky planet. And I would like to discuss a little bit this. So you may have heard maybe the oxygen is a very key molecules to find. Actually, we have to be careful. It's true, it's a very interesting molecule, but oxygen doesn't mean life, while on Earth right now, we have produced, life has produced the oxygen. Because you can produce in very different, and that's an example from Wikimedias, of the productions of oxygen into an atmosphere of a planet where you have no life, but you have some specific geophysical pattern that is mixing or breaking the molecules. So bear in mind, if you have water and you break the molecule of water, you end up with oxygen. And you can even have CO and CO2 and you can break it as well, and you end up with oxygen. And if you have some water mixing, you produce kind of interesting mix of everything. So be a little bit careful about meanings that discovery life. So what I would like to tell you is how we're going to do that. And we may not do exactly what you have in mind through detect life, but we will have to treat the planet as a global entity with life part of it, but not essentially. So understanding whether there is life on another planet at the end means understanding the planet itself and how everything goes together. To give you an example, what we're going to do, I have to show you a bit, if you're not familiar, the history of Earth itself. So when you go back to the history of Earth, you will have different phases that has been identified. Well, early on, it's astrophysics. You build up the planet, essentially, what we call the nebular phase. Well, when you assemble the Earth, it's very hot. So you have impact, you have a hot magma. That's exactly at that time that one of the big impact hit the Earth and made the moon. The moon came from that time, very early on, about 20 million years old after the formation of the Earth. The atmosphere you have is very different. You see from today, hydrogen, helium, H2, CO2, and depending on how many material is falling, there's a lot of what's called deliveries, a lot of comets falling at that time, really a lot of them that enrich in carbon. They're full of carbon in this comet because of the CO2. Remember, the CO2 gas collapse farther away, it makes a lot of comet with CO2 snow. This CO2 is coming because it's coming into the planet and they melt, and then you have a lot of carbon delivery at that time and water delivery as well. So everything cooled down. You start at some point the volcanic activity, you produce CO2, recycling the CO2, SO2. Somewhat the magnetic field start at that time because you start, you don't have any hot magma, there is still partial melting, but you still have a core, and you start the magnetic activity. And then life is starting somewhere here and is changing the atmosphere of the Earth. Well, if there is no life, you will also change the atmosphere, but you will not have a call of biological driven atmosphere like we have today. We just have a mineral atmosphere. So this is a global process, and you cannot understand one bit without understanding the other one. So when you look at what it means actually in terms of these detections in the atmosphere, you can connect the amount of gas, which is up here on the left with the time. This is when you form the Earth. This is just now that you have along the history of the Earth. When you start the Earth, you have a lot of carbon dioxide, and then the carbon drops and quite a lot. I know it's coming up because we are bringing the carbon dioxide from the inside into the outside. The oxygen was almost non-existent at the beginning, and then you have this huge rise of oxygen. That was a problem because actually at the same time the carbon dioxide was dropped, and the greenhouse effect that was related to that dropped as well. So we had an experience at that time that was dramatic for life of snowball. The Earth may have almost became inhabited at that time because it frost, and some piece of rock happened. We don't really know exactly what, but very likely volcanic activity managed to bring back a lot of CO2 and SO2 into the atmosphere and making the partial melting and getting away of this trap, gigantic trap. So when you form life, and that must happen at that time, it doesn't mean that life will survive the story of the planet? Well, what you can do at the same time, you can imagine the kind of signal you would have in the atmosphere. So now imagine a telescope observing many different planets and looking at that. The early Earth, which is called the Archean Earth, would look very different from the Proterozoic Earth, which is when you have life. And it would be very different from today. So you can imagine by looking at the atmosphere, it's not about looking at life. You look at the Earth as a global entity, and you would learn, if you have many of them, you observe many of them, what they look like. Maybe they would all look different, or maybe most of them would look the same. That's something that we'd have to find out. But that's what is going to happen in the future. And of course, on the top of that, you have a buildup of life. Now, the buildup of life is not very well understood. It's a complex process where you have to start with very small molecule at the beginning and come up with a chemical pathway that is making the building blocks, assembling the building blocks, building some kind of replicating until you have something alive. Then to have this happening, it has to happen on the planet. So the idea is, to some extent, if you understand the planet and study the planet at different phases, you should be able to understand some of these key steps. And this is why it's so exciting to go on Mars, because Mars had pretty much a similar evolution than the Earth for the first billion years, but after stopped because there is no plate tectonic beyond about the first billion years happening on Mars. So it's essentially an imprint of a very specific moment on Earth that has vanished, because on Earth there is always this recirculations, the plate tectonic, and any chemistry on the surface of the planet had just been recycled, and we have no idea what it is. So this is why we're so excited to go to Mars right now, and one of this beautiful Mars picture. And we're even more exciting because we are there. And if you just pay attention to the structure, you will recognize without any doubt that you have here river flow and then some kind of a lake and a delta here, and the robot came here and is going up there along the way and is going to study the whole chemistry that you had along this way. So what you have to imagine is 4 billion years ago, the landing site of the robot was about like that. And we landed in the rest. Of course, there's no water right now, certainly not like that. But we are going to look and study the chemistry, because we do believe that it is in that kind of places that the early chemistry of life happened. So it must have left something, some traces, some mixing. I don't think we're going to find life. I mean, if you believe we're going to find life on Mars, I think it may be the wrong way to see it. But we're hoping to see some indications that there has been the beginning of life on Mars, and certainly helping us to understand the origin of life on Earth. So bringing back, and then this concept, imagine we do some, and bring back the image I had before, and I try to move to then, imagine you have a machinery and then you can observe the planet and try to identify the nature of the atmosphere of this planet, because we don't have really atmospheric feature very well visible on Mars. We have to bring the rocks back, and we're going to do that and study the mineralogy on Mars. But if you have plenty of planet to observe that is not very different from the Earth, well, what you can imagine is, coming back to my diagram here, you could look to specific feature, and you see here, look at just these places here. Here you have a very specific gas with CH4. When you observe the same region in wavelength, which is close to the red end of the visible, you only see water. And when you observe that now, there is so much oxygen that you see a lot of ozone in this region. So just to give you an idea that by observing the feature, you can learn something about the geophysical episode you're talking to. And that's a bit what I'm doing in this picture here. When you have the wavelength of them and a kind of machinery we would have in space, which doesn't exist, and we will have to fly it in the future, maybe in 20, 50 years. But looking at specific molecules that you may have in the atmosphere, and what you have, the small icon you have here, tell you what we think this specific molecule we're talking about are connected with. So some of them are connected or identified as a prebiotic signature. Others are related to an impact signature or a volcanic activity or very high energy lightning happening on the planet, or a massive impact that is happening at the same time on the planet. So you can play with all this. You can play with all these observations, and you imagine that you're observing many different planets having different conditions. You start building a scenario for the origin of life, and the scenario that could be in a way compared to the situation on Earth. So you see, it's an amazing time we're living, because we are starting exploring the solar system, bringing rocks together. And I mentioned Mars, but you can talk about Venus. You can imagine to go to Titan, some of the satellites of the giant planet. You can go to Enceladus. In this case, you would look for different chemistry of life. And that's something that will happen. It will happen because we now have the capability to do that. But at the same time, we will have almost an infinite number of words on other star to study, for which we will use some imprint of the traces of the geophysics on life to understand what has happened. So I will stop here. I hope I share enough of this enthusiastic development. And the interesting bits of this is, you would have guessed, it's not only about astronomy, it connects also geophysics, chemistry, and biochemistry. And there is a lot of interest right now from different views and different angles to join this massive program that started essentially with the beginning of the first exoplanet findings. So I stop here, and I will have time for any question you may have.
Didier, thank you very much for this exciting and provocative lecture. It was really interesting to see how many developments and how so many fields of science come together to try to tackle these big questions that people like you and others in other fields have now. Just a question, and then I pass it to I will do a question, and then I pass the word to Rodrigo. The question I have is, there are these thermal vents at the bottom of the oceans. What is your opinion? What is the feeling in the community regarding if life emerged first on the surface of the planet and then came to the bottom of the ocean, or if life came from the bottom of the ocean and then came to the surface of the planet, at least for planet Earth? What could you say about it?
So that the bottom of the oceans, dark cities, all this has been in the literature for some times, and for good reason, because if you want the chemistry to happen, you need to break energy barriers. You need some catalysis mechanism, and there's not much options for the catalysis. Is either you have heat. When you do chemistry, you have to warm, and that's what you have for free, or you need some kind of energy, and in that case you use light. And what is interesting about this origin of life on the surface of the planet, which is something that started to develop about 5-6 years ago, is for the first time there is a series of chemistry that have been developed, demonstrating that there is a pathway to life starting from scratch and having the molecule you have on the surface of the planet, and then using just the UV radiation that you have for free from the stars. That's a big change, because the idea that you would use thermal vent is essentially built on a comparison mechanism. So you have some of the mechanisms that you need for life, and that there is some comparison similarity, but there is no chemistry that has been developed really that is building up the life. So I don't really know what will be the outcome of this. I think the end game is when we will be able to make life in the lab, and people right now are seriously working to bring together all the main components of life, using the idea that there must have been some chemistry on the surface of the planet, around lake and river, using the energy of the sun. The sun is there, so it's certainly easy. And what is good with the sun is you can have a massive energy productions at a global scale, While when you implicitly need the bottom of the oceans, you make some assumption of very specific locations. So I don't know. I think the debate is in the air, but there is a growing number in the community, and especially the biochemists right now, that seems to believe that the origin of life on the surface of planet is certainly very interesting to continue and to push further. And that's something that the Mars missions should tell about, because there is a series of predictions, and that's the good stuff I like as a physicist. There is prediction about this chemistry of life on the surface of the planet that is testable, while there is no prediction at all from the vent. So we'll see, and you see how science goes. So I think it's a new idea that we will need to push forward. As an astronomer, I like the idea of the surface of the planet because we can provide a lot of data on that, and we can challenge some of the productions, we can challenge some of the parameter. And one challenge that I had is whether there is enough energy with the sun to produce the relevant chemistry. And we did test that actually by bringing astrophysics equipment. I did that with some of my colleagues here in Cambridge, trying to calibrate to understand whether it works. And actually it works with the sun, but it does not work for the small stars. So there's interesting conclusion of this work. If you believe to the origin of life on the surface of the Earth, that seems to produce the 20 amino acids at least, I think it would not work for the M stars. You have to find another mechanism for the life on the M stars. So maybe there is plenty of pathway for life, or maybe there is only one. And we need it narrows down the chemistry. So this is the global situation right now on that topic.
Thank you very much, Didier. Rodrigo, do we have questions?
Yes, thank you very much, Professor Queloz, for your nice talk. We have a couple of questions. The first one is from Saul. He asked if life on Earth began on water, and this graph shows that how the density of water on Earth did not change during its history. How important is water?
I missed what you said.
Okay, sorry.
Density of what?
How important is water to life?
Water. Yeah, water.
Water.
Change. No.
And how likely is to find a planet with a water density similar to Earth?
Well, you don't need that much water for life. You just need enough. Well, the water problem, I mean, the water issue is actually even more complicated, because water is essential for the plate tectonic. You don't have plate tectonic, you don't have recirculations, you don't have CO2 recirculation without water. So you need water, but the water itself is found everywhere. So water is, people believe water is magical. It's not. Water is the simplest possible element after maybe the hydrogen and helium you can find everywhere. You point a radio telescope to any molecular cloud, you will find water, you will find organic molecules. So all this is everywhere. So carbon, water is everywhere. So you do have water. You do have water deliveries from the outside, but you do have a lot of water which is embedded into the rocks of the planet that is going to resurface when the planet is cooling down. So if you don't boil the planet, you never lose the water. So the understanding right now is essentially the water that you got at the beginning of the origin of the planet, including also the early delivery, stay forever. And that's the water we have.
Okay, thank you very much. We have another question from Thomas. He says, how can we make sure that we are not limiting our scientific research and observation, our cognitive bias, based on our understanding as human of life as Earth-like? I mean, carbon-based. Is there any bias in that? How are your thoughts on that?
Well, I think this is clearly, we have to acknowledge that we only know one planet with life, and we only know one life. So we are extremely biased in our starting point, because that's the only thing we have. But at least we have something to start with, and we should accept this limitation. It doesn't mean we should be blind, but that's something we have to deal with. So that's a very serious limitation, and I agree. No, speaking about the carbon, I think my perspective is very simple on that, is why do you want to make life with something which is rare? Why you have carbon everywhere? So carbon is the idle component to build life. It's not the only one. You need a couple of them, and carbon is everywhere. You point a telescope, a radio telescope, you see carbon everywhere, and the main production of the stars, and you have carbon everywhere, and that's a magical, I think, element. So I don't see why you would do something more complicated when you can make it simple. So I think the idea that you build life on other things of the carbon is ridiculous, because I would start first building life on carbon before doing anything else, because that's what I have almost infinite. Now, whether you need the same kind of structure, if you think about the DNA and the RNA, that's a much more difficult question here, because life as it is today is the end of a very long processes in a way, and that experimented a lot of different pathways very likely, and turned out to find out the most optimum way to build life, and is the winning way. Is it the only way to do that? So is it following a kind of what's called in physics a minimum energy path, and that's the only way, because that's the best way to go through. If you have two mountains, you have a pass, you will go to the pass. And even if you don't know the pass, you will try, and at some point somebody will find the pass and you will go through. So maybe there is only one way to do that, or there is plenty of way. And that is why I think the day when we will have demonstrated that we can make something alive, what does it mean in a lab? Then it will be the day when we'll begin to explore really the diversity of life, and whether there is other way to end up with life. But at that time, it means we will have reached the second power of God. We already have the destruction power, the thermonuclear weaponry. We will have the second one, which is to make life. And that will open a lot of questions, I think, the day when we can make life from nothing, essentially. So there is still a long way to reach that level. Whether it will happen tomorrow and in 300 years, I don't know. But what I do know is there are people seriously working on that right now. And there's a lot of progress on the various elements that need to assemble to have something which is considered being alive. So the limit is real, but the fact you limit it doesn't prevent you at least to start doing something for what we know, bearing in mind that it may not be enough. That is why going to satellite like Titan or Europa or Enceladus is very interesting, because for this very satellite, the idea of the origin of life on the surface of the planet doesn't work. You have a different situation, because you have a heavy ice cap on the systems. The water, you have a mixing, you have methanes, you have water, you have a different chemistry there. So I think we should really have a look there, whether we are finding fascinating new chemistry that may be connected to something alive. And bear in mind that you can have something alive. It does not mean that you will build up the multicellular life, because that's a big invention. The fact you move from something single to a couple of elements that are going together, losing the identity and behaving like a global entity, it's a massive invention for life. And whether it is already happening, or whether you need something specific, whether you need a moon to allow a big tide, to allow some small living organism to get out and start walking on the surface of the continent. There is so many questions here that I'm afraid, and it's difficult to answer, but at least you have to start somewhere, and that's the way people are addressing the problem right now.
Okay, thank you. We have another question from Valeria. She's asking about exoplanets. Exoplanets are being detected by the measurement of small periodic changes in stellar radial velocity, and this is produced by the orbit of the planet. So she's asking, what is the relationship between the Doppler effect in this stellar radial velocity, how it is useful?
Well, what you do to detect the planet, you detect the change of speed of the star. So when you have the planet going around, the star is going back and forth, and in front of you, behind you, and then it keeps going back and forth. And to detect the speed, I think you use the what's called the Doppler effect, which is a change of the wavelengths. Very tiny change that you have to pick, but that's how we're using the Doppler velocity, is to compute the radial velocity of the planet. And of course, we have to be careful when you do that, because the atmosphere is not static, and the atmosphere has some motion as well. So this is the reason why right now we are facing difficulties to detect very tiny change in the radial velocity, because it's mixed with the intrinsic variability of the atmosphere of a star.
Hey, thank you. We have another final question, maybe. This is about the James Webb Telescope. Which one, I mean, from your point of view, will be the major breakthrough that this telescope, I mean, we are all excited about James Webb Telescope, and it is about to be launched. So which is your perspective about
we have to face the reality that James Webb has never been built to detect planet. So it has been a late fix to make it work. It's not a telescope designed for that, but of course, because it's a 6-meter size dish telescope, because it's working in the infrared, there is plenty of program that can be done, which is in a way doing what we've done, but trying to observe a bit smaller signal on smaller stars. So James Webb, I don't think James Webb will be magical for exoplanet, but of course, when you have a new machine that has access to bring you new data, which are better, there will be surprises, and you should expect big discovery. But I would also bet on the ground-based telescope, because the ground has made a big step forwards right now. We're building a new generation of gigantic telescope. In Chile, this 42-meter. There's a telescope in Hawaii that would have more than 30 meters. So all this kind of telescope, I mean, can do, again, similarly to James Webb, will explore, I think, some of the atmosphere of this planet, and we have some capability to do some direct imaging, which is not something that James Webb will have. What I'm betting right now is the next generation. So people are really trying to develop concept to fly the James Webb for exoplanet. So there is a couple of names, Life, Luvo, there's a couple of names that people are flipping around. And that will be the big breakthrough, because this machinery will be built from scratch, optimized for exoplanet. And since it takes 30 to 50 years to develop some kind of concept, I think we will just have to accept that in the meantime, we will do what we can with James Webb, but people is eager to start building the next generation of satellite and telescope. And that's what I'm really hoping will come. So this is where I expect the main breakthrough with the next generation.
Hey, thank you very much. So because of time now, I'll leave the space to Eduardo again. Thank you very much again. And Eduardo.
Thank you. It was a pleasure. Good luck. Have a good day.
So I am closing now. Sadly, we have a couple of more questions, and the question I have to you is if you want to answer just one more question, or if we close it.
No, I can still answer a last question. After, we'll have to go because I have another meeting in 15 minutes.
No problem.
But that's okay. Yep.
Thank you very much for your patience and time. Yeah. The question is shortly, what do you think if we can predict another change on the Earth's atmosphere? That's from one of my students, Edgar. And I will make a slash on that question. What do you think of what we're doing to the planet? Can you comment on climate change or something?
Oh, well, okay. Well, I can certainly comment on it. I think that's pretty clear that, by developing the agriculture, by having starting to have herd and to have cow and to have sheep and to have all the animals, we are changing the planet, and that's pretty clear. It's not something new. That's something that started, I think, 10,000 years ago, and now it just has accelerated because now we're digging out a part of the embedded CO2 that was inside the planet, and we bring it into the atmosphere. So of course, we're changing the atmosphere of the planet. That's pretty clear. Now, it has dramatic consequences on the society. I don't think it has dramatic consequences on life. We're not going directly to affect life. I mean, we're going to increase the temperature of the atmosphere. We're going to rise the height of the oceans by millimeter, and that will have dramatic consequences on the society, because a lot of the cities that are actually next to the oceans, nobody could live in these cities because it would be underwater. So this is actually the big problem. And it's not itself the fact you change the temperature, it's the fact you are bringing instability in the global world by bringing at a massive scale society problem like migrations, and the expectation there will be 1 billion people that will have to be relocated because of the change of the age of the ocean, or some place on Earth that nobody could live anymore because it's too hot. And my fear here is how we're going to react to that, knowing that we have the power of destructions. So we could imagine that this could very easily trigger war for water, war because there's too many people that want to change from one country to another one. And that is where I'm getting worried about, because we're creating so much instability at the high scale and the global scale that it could be the end of our species, because we're going to end up with a massive thermonuclear war and killing everybody, essentially. Whether life will survive, it's not very clear. Maybe some kind of life will survive, and it's difficult to extinct completely life, but certainly all species would have self-destruct. So that is why I'm getting worried about the global warming. It's because it's not taken seriously enough as a global social impact. And we keep talking about scientists and prediction. I think all this is just a big joke. I think the global warming is understood since 30 years. We know exactly what's going to happen. The problem is nobody is ready to accept the social consequences and the economical consequences. So it's time now to bring the global warming topic out of the science, but in the society. And it means everybody, in a way, have to change the way they just work and live. We cannot continue like that. We cannot keep traveling the way we do travel. We cannot use the energy the way we use it. We cannot eat so much meat that we keep eating meat. I think our society has to evolve if we want to survive. So that's my own perception of what's going on. Sorry, not to be very optimistic on that.
Thank you. No, thank you, Didier. It's very realistic, I will say. I agree with you entirely. And sadly, my home country, Guatemala, is starting to have lots of immigrants and lots of problems because side effects of this global climate change. Yeah. And it's for many of the authorities hard to realize that it is happening and we should do something. So Didier, I know you are very busy, and you have no clue how happy I am that you accepted our invitation on behalf of my students, more than of myself. It's really great that you accepted our invitation.
It's a pleasure. I think it's important to connect with the students, because you students are the future of our society, and you are the blood of science. And we need people, I think, in science. We need people that have scientific background, even if they don't do science. It's even more important if they become president of states, of countries, because this is where they can really understand what's going on. So I really enjoy doing it.
Thank you very much. I want to thank Rodrigo. I want to thank some of the authorities of the universities that join us, the students and colleagues. Really thank you. And we send you a big hug. I am in Switzerland. I send you a big hug from Switzerland.
Okay, you're in Switzerland.
All my students send you, and Rodrigo and my colleagues are sending you big hugs from Guatemala. Thank you very much, and I look forward to meet you again. Bye-bye.
Thank you, bye.